Okay folks, we are going to look at, still looking at vertical changes or vertical transformations to the sine curve. The mother curve for the sine, all sine curves, is the curve y equals the sine of theta. And these are all transformations of that curve. Now again, to remind you, we're sketching over a different domain. We're starting at minus 180, finishing at 180, so you're not going to move outside of that domain when you draw your graph. So let's put in the points for sine again. We know them by now. I'm going to change this to a 1 and that to a 2 and a 3 again. So let's all do that on our diagrams. And let's mark off the mother curve. The mother curve would go to 1 and return to 180 there, and then continue to 270 and 360 if we were sketching outside of this domain. Okay, so the domain is restricted, so we go to here minus 90, and the dotted line then indicates the mother curve for you. You don't always have to draw the mother curve first, but draw it in pencil, and once you've drawn the rest of them, just erase the pencil. Okay, so again I'm going to ask you to draw this graph, to find the relationship between those two graphs, and then to draw g of theta. Now you'll see the one says twice the sine of theta minus 1, so I'm first going to affect the vertical stretch of factor 2, meaning I'm going to take the mother curve and multiply all its y values by 2, and then I bring the whole graph down 1 vertically. Now this one, you'll just see that the signs are different. That's a big hint. Okay, so folks, pause the video and then sketch the two curves. Okay, let's have a look. You've done your mother curve. We've indicated where the mother curve lies. Let's affect the vertical stretch first, and then we're going to translate. So this y value doubled stay where it is, because the y value is 0, and 0 times 2 is 0. The y value for this point on the mother curve needs to double, so the y value goes to 1. It now goes to 2. And then here it crosses the axis again. Here the y value is minus 1. It goes down because it multiplies by 2. It moves to minus 2. And then here 0 multiplied by 2 is then the vertical stretch. So far what we've done is we have basically applied the stretch factor of 2 to the mother curve. I'm still dotting it because it's not my final graph. Now each of these points that I've doubled, and all the y values rather, should now be diminished by 1. I take 1 away. So the y value for that point is 0. It goes to minus 1. The y value here is minus 2. I take 1 away. It goes to minus 3. The y value is 0. I take 1 away. It goes to minus 1. And the same there. Take 1 away. Here I take 1 away. And now I can draw my final version of that curve. Now remember, it looks the way it does, folks, because I am sketching over a limited domain. The period is still the same. Nothing has changed. So here my exit point will be 180 and minus 1. Here my entry point will be at minus 180 and minus 1. And then my minimum would go to minus 90 and minus 3. And my maximum would go to 90 and 1. Okay, so the curve first of all stretched by a factor of 2 and then moved down. The first one. This is f of theta. Now if I look at its relationship to g of theta, let's just see what this relationship is. If I take g of theta and I remove a minus from it, I get 2 sine theta minus 1. And 2 sine theta minus 1 is the curve I've just drawn. So what is happening here? To get to g of theta, I must multiply all the y values on the black curve by a minus. So in other words, what is happening? It's reflecting in the x-axis at this point in time. So if I now change this y value to a minus 1, it would lie over there. Remember, I'm timesing it with a negative 1. I'm reflecting it in the horizontal axis. This point would then, if I times that by minus 1, would go to 180 and 1. The point here is minus 1. Times by a minus would go to the positive value of 1. Be careful here. The y value here is now minus 3. If I multiply it by a minus, the 90 goes to positive 3. The x values don't change, the theta values. It's the y values that do. If I multiply that y value with a minus 1, then that will be at 1. And this is how you generated g of theta. G of theta is a reflection of f of theta in the x-axis, or the theta axis. I had a bit of a bump here. Okay, now folks, you can see the beautiful symmetry in the pink graph and in the black graph. They are symmetric in the mirror line through which they were reflected. Here the x value stayed the same, the y value just reflected over the x-axis. Here the x values, all the x values stayed the same, the y values reflected. That's quite clear what happened there. Here I have 90 and it's now reflected to the negative, and this negative point has reflected to 180 still in the x direction and 1 in the y direction. Okay, so folks, be careful how you affect the change. Now I can take an eraser and take my dotted graphs away if I want to. It just depends on what you want to do with that. I hope that that made perfect sense. Now, what we saw in the very first video, let me just remind us of that. In the first video clip, we saw what happened to sine and cosine and how they're different. So cosine happened 90 degrees before sine. Okay? Where sine has a maximum at 90 and 1, cosine will have its maximum at 0 and 1. So the sine graph translated 90 degrees forms the cosine graph. Very, very important to realize that, and that also is the basis for your complementary ratios. So everything that we've learned about the sine graph is true for the cosine graph in terms of the transformations that we've looked at.